Hello, students, and welcome back to Study Room. So, today we're going to start a brand new chapter called Magnetic Effects of Electric Current. So, I'm sure all of you must have played with those black magnets, those two pieces which you throw up into the air and they join together, and you play a lot with them. I have. I don't know if you have. I hope you have. It is actually really fun. Or you must have seen or saw or heard people call, oh, this is a magnet, this is a fridge magnet, this is a magnet that you can put on the fridge. People bring like souvenirs from outside of India, there they go, right? So what is the difference between that and the title here? We're not talking about those kind of magnets. What is written here is magnetic effects of electric current. What is current? We have already studied in great detail that in a circuit we have a battery which is able to maintain a potential difference, and when we know that there is any difference, there is some kind of current that flows, be it air, water, and in case of a circuit and a battery, it is current, it is electric current that flows, right? So we know all about that already. Now we're going a little step further. So you'll see that physics is actually very systematic. Physics doesn't directly teach you very high level stuff, it will teach you basic stuff, and then you'll use those basic stuff, all subjects actually, not just physics. But here you should now try to relate everything that you have learned to what we are learning now. Okay, so we have learned electricity, we have learned current, and now we're going to see how is that phenomenon that we use in magnets, that we see in magnets, the two magnets sticking together, but electricity is just current, electricity flowing through wires. Like, how are they related? You must think about like that, right? That is what we're going to look at. How are those two things, which seemingly seem to be worlds apart from each other with no connection, they are related actually. Okay, so first we'll actually see what magnets are, and then we'll get to the current part of magnetism. Okay, let's start. Okay, so how many of you have seen this photo, or how many of you have seen something like this anywhere? It could be in some of your geography books or any of your social science books, or even on the internet, in some movies, maybe. Do you know what this is called? So, for those of you who have never heard about it, these are actually called the Northern or Southern Lights. Or if you have heard about their names, they are called Aurora Australis or Aurora Borealis. I'm sure you must have either heard it somewhere or read it somewhere, right? So, this phenomenon is actually related to the magnetism of the Earth. So, you might not know yet that Earth itself acts like a magnet. You know that we have one North Pole and one South Pole, right? Why is it called North Pole and South Pole? Because actually that is like the magnets North Pole and South Pole. So don't worry, this is all going to make a lot of sense when we study more about magnets. But you should know that this beautiful natural phenomenon that happens in the sky is actually related to the magnetic field of the Earth. Okay, great. Let's move on now. Okay, so now we're going to move on and see just how that beautiful phenomenon looks in the sky. Okay, let's go. This is a scene from the Arctic and Antarctic circles. That is the region where the Aurora Borealis and the Australis are formed, right? So, this is how it actually looks. It's also called fire in the sky. This is actually like a once in a lifetime opportunity. If any one of you gets to see it, it is considered to be so special, so special. Just look at it. We're just used to seeing colors of the sky like pink, the sky gets a little orange, but colors like this, like blue, purple, green, all of those beautiful colors, yes, that is the Aurora Borealis. And similarly, its sister phenomenon is Aurora Australis. Okay, let's move on with our study of magnets now. So now we're going to look at some examples of magnetism in daily life. Okay, this is something that you all have seen around you. What is the first picture? What does this picture say? This picture shows you a computer hard drive, right? This also used the phenomenon of magnetism in storing the data in it. What is this second image? This second image, what does it look like? What does it look like a scene from? Does it look like a school? No. Where does it look like? It looks like a hospital. So this process is actually called taken an MRI. which means the full form for this is magnetic resonance imaging. So you don't need to know about what an MRI is and how it works, but I'm just telling you one very crucial example or a very crucial real life application of magnetic field. So magnetic resonance imaging. So in this process, basically very strong magnetic fields are used to send into our body, and they are reflected back by our body, and it gives us a clear image of, basically takes a scan of that body part that you need to study, or the doctor wants to see if there is any problem or any unwanted growth or anything. Okay. Now, what is magnetic field? All of that we're going to study in detail, but this is just to give you an example, just to start showing you how magnets work, where magnets work. Magnets are there around you in your real life also. Okay. This picture, I'm sure all of you know. What is this? This is a fridge or a refrigerator, and these small trinkets, these are the fridge magnets that you get all around the world, and people bring home back as souvenirs from different countries also, right? These make use of the property of magnetism, and these have magnets in them. Now this, what do you see this? You see this huge crane pulling up this something very heavy. It looks very heavy, like metallic, huge, heavy, right? That is also this part. This part, I don't think you can see, but this part, if you can see, I'm circling this part above that huge metallic thing is what contains the magnets. Now you'll see why it actually sticks to it. There is no fevistick or any glue used there. It is the property of magnet. It is the attractive property of magnets that is used there. How that works and everything, we'll just see. Okay, let's go. So magnetic poles. What does your PPT say? Your PPT says that the magnetic pole is the region at each end of a magnet where the external magnetic field is the strongest. Now this is an example of a bar magnet. We'll study more types of magnets, but this is the most important and most commonly used magnet. This is the basic magnet that you all start studying with. This is called the bar magnet. It can be represented in a horizontal or a vertical way, however you like it. So this N is the north pole. It stands for the north pole of the magnet, and it is divided, and the next end is the south pole, obviously north and south, right? So basically what happens in magnets is that they have a field. Now what does a field mean? Field is basically means an area of influence. Okay, so around this magnet we'll see what the fields look like, and how, is there a direction to the field, how does it work, that all we'll see. But here, if this is a magnet and this is the north and south pole, right now all you need to know is that the magnetic field is the area of influence, and it is not constant. It is not constant. It depends on distance from the magnet. Just think about it. If everything depends on distance, right? If I'm talking and you're standing, say, 1 feet away from me, and we are talking like that. If you go stand 6 feet away from me, my voice will become lower for you, right? Even if I'm speaking at the same pitch and at the same volume I was, if you keep moving away and away from me, wouldn't you start hearing me less? And if you go stand 1 kilometer away from me, even if I'm using a loudspeaker, you would not hear me, right? So like that, magnetic field also, the strength of the magnetic field. Now magnetic field means the area of influence or the influence of the magnet. So what is a magnet? Magnet is that bar, or it should be shaped. It can be shaped in any, it can be shaped in any form or shape, and it has two poles. You need to know, this is very important, that it has two poles, the north pole and south pole. All magnets, no matter what the shape, size, what type, all these magnets have two poles, which are north pole and south pole. There can't be a magnet with just north pole or just south pole. These both go together. Okay, and they exert a magnetic field around them. Okay, so you will see how it looks like and what happens. But right now you can just imagine as if I'm just standing like this. I'm standing with my arms out, and I start rotating like this. I start rotating like this, okay, in complete circles. then if I am the magnet, this span of my hand will be my magnetic field. Okay, so magnetic field is basically that influence that the magnet has. Okay, and similarly, because my hands can't extend till infinity, my magnetic field only is valid up to a distance, and it keeps decreasing with the distance. Like if someone is very close to me, I can hit them with my hand while rotating very easily. If they go a little far, I can maybe stretch my hand a little bit and rotate. If I'm at one place, stretch my hand a little bit and hit them. But if they go a little more far away, I would not be able to hit them. So what is happening? My span is decreasing with distance. So similarly, the magnetic field, the strength of the magnetic field of the magnet decreases as we go far from the magnet. It decreases as we go far from the magnet. Okay, let's move on. Now, okay, so in this picture, do you see this? I explained this to you. This is the bar magnet. What is this thing called? What is this called? Do you know what this is called? This is called a compass. And this compass is nothing but a magnet in itself. So you must have seen in movies or in books, you've seen that, sailors use compasses to determine which direction they want to go in. So this compass, this needle of the compass, this needle of the compass, it points north and south, which means this red end, it points towards the north direction, and this south end points towards the south direction. Now, which north and south is this? It's the north and south of the earth. So you know, right, in maps, while you're reading maps or in Google Maps, it tells you go towards north or you go towards south, right? So that north, south, east, west is determined by the north and south pole of the earth, or the north and south depending on where you're standing. So this is the important point here, that how is this able to align itself to the magnetic field? Because the compass needle in itself is a magnet. Okay, this is the point that you need to know right now. Needle is a magnet itself. Okay, great. So here there's a question that says, why does a compass needle get deflected when brought near a bar magnet? So if you've ever played with those two little black oval pieces, you remember these, it looked like this. Each magnet looked something like this, and they were both black colored, and you used to throw them in the air together and they used to stick together. So if you've ever played with it, or if you ever get any chance to buy magnets around your house, go and buy them and get them. It would be very easily available to you. It would not be that expensive also, and it would make things clear to you when you're studying it. So what happens is, if you're holding one magnet like this and the other like this, okay, you're holding them in this position. Look how I'm drawing it, like this, not one over the other, but one in front of the other. Okay, and you bring them closer like this, right? So at one point it would seem as if they are attracting each other, they want to be joined together. But when you keep one of the magnets like this and you turn the other magnet around, what happens? If you try to bring them closer, it would feel as if they are trying to go apart from each other, or what is the word for it? Repel each other, right? The word for wanting to come towards each other is attract, and the word for going away from each other is repel. So what is happening? Magnets definitely have a property to attract and definitely have a property to repel each other. Why that happens, we are going to see. So you're just going to learn why actually that happens in a bit, but this you have to keep in mind, okay? This thing about magnets that I told you by changing their direction, okay? So this would make more sense to you when I use it in that slide when I teach you the property of magnets. So here, why does the compass needle get deflected? We need to use this because we just said that a compass needle is also a magnet, right? So as magnets attract or repel each other, the compass needle deflects when brought near a bar magnet. Okay, all of this is going to get a little more clear as we go step by step. Okay, don't worry. Okay, let's move on. So now we're going to come to the real part that we need to study, that is the magnetic effect of electric current. So it was observed by a scientist called Hans Christian Ørsted. He actually accidentally observed this discovery of the phenomenon that electric current actually has magnetic properties was a complete, accidental discovery. So this scientist, Hans Christian Ørsted, was actually performing some electrical experiments and he happened to have a compass just near him. So what happened was that Hans Christian Ørsted was actually performing an electrical experiment where he had this circuit and he accidentally kept a needle compass beside it, basically. So the compass obviously has this compass needle inside it, and we just studied that a compass needle is a magnet in itself. And we also studied that a compass needle gets deflected when a magnet is brought near it. So that makes sense because a bar magnet has a magnetic field and a compass needle is also a magnet, and we know that magnets when brought near each other, they either they want to come towards each other or attract, or they want to repel, right? That makes sense. But why would the compass needle get deflected by when it is kept near a wire carrying electric current? There is no magnet there is no bar magnet, there is no other magnet kept anywhere near. So that is how it was accidentally discovered that electric current also actually gives rise to a magnetic field. So that is what our study is going to be all about. Okay. Now, this is what I was talking to you about. These are the properties of magnets, and now it would make more sense about what I was saying about the magnet, wanting to attract each other or repel each other. These are the properties of magnets. There are two properties that the first property says that opposite poles attract and similar or same poles repel. Attract, basically, you know what attract means. If you're attracted to someone, you want to go towards them, you want to talk to them. So attraction basically means wanting to come towards or near each other. And repel means like when a lot of you see like vegetables made at home, you're repelled by it. You're like, no, we don't want to eat that. We want to order something from outside. So that is what is repel. Okay. So this is the property that when opposite poles are brought near each other, they attract, and when same poles are brought near each other, they repel. What does this mean? One pole is north pole and the other pole is, wait, I'll make it in a bar magnet form only. So this is a bar magnet. One pole is the north pole and one pole is the south pole. So these are the two different poles. So when north pole is brought near south pole, would they attract or would they repel? Look at these 2 points that I have written here on the left hand side. I wrote opposite poles attract and similar poles repel. Are north and south opposite poles or are they the same poles? They are the opposite poles, right? So they will attract. Now, if north pole and north pole are brought near each other, the north pole of two magnets. Now, refer to this photo that is given to you. The first one I have drawn here, north and south. So there are two bar magnets, bar magnet 1 and bar magnet 2. So one bar magnet's south pole, you are bringing near the north pole of the other bar magnet. So they will attract. There is going to be attraction. Second case, I'll write with it only. North pole of one magnet is being brought close to north pole of the other. What is the property we learned? This is same poles or this is opposite poles? This is same poles, right? Both are not. So they are going to repel each other, or there's going to be repulsion. They want to go away from each other. So north and north, if they are brought together, they repel. Now again, one magnet's south pole and the other magnet's south pole brought close together. Same poles attract or repel? They repel. So there is repulsion. So south pole and south pole, when they are brought together, also repel. Okay, so that is the major property of bar magnets, that you, not just bar magnets, any magnets that you have to always keep in mind. So that's, now you can link it to the compass and the bar magnet. Think about, if the compass, the north pole of the compass is brought near the north pole of the bar magnet, there is going to be repulsion, so the compass is going to be deflected. If the south pole of the bar magnet is brought near the north pole of the compass, there is going to be attraction. So there is still going to be some movement, so that the compass needle wants to move towards, they want to be attracted to the opposite pole. So that is why there is a deflection in the compass needle. The bar magnet can't move, right? It is heavy, it is stationary, but the compass needle is free to move, right? Let me show you a video of how a compass needle actually works, so it would make more sense why the compass needle gets deflected and not the magnet. Okay, so this is an animation to make it more clear to you how the compass actually works. So just keep looking at the needle of the compass. Look what is happening. It is moving to the right and to the left, right? That is called the deflection in the compass needle. So this needle is free to move completely like that. It can go completely 360 degrees and come back, right? See, completely took a full circle rotation and it came back. So that is how the compass gets deflected. Now think about it. The red side is the north pointing side. If the north pole of a bar magnet is brought near this red side of the compass needle, which is the north pole and south pole repel. So this north of the compass would completely turn around because it wants to be away from the other north pole, right? They repel each other, similar poles. Similarly, if the north pole is brought near the south of the compass, they would attract. So the compass needle would be in that same area and try to go near to the bar magnet. This is what you need to know about a compass needle and a bar magnet. And now it should be more clear to you how it was discovered that electric current also has some magnetic properties, because when the compass needle was kept near a current carrying wire, it got deflected. So Hans Christian Oersted started thinking that why is the needle of the compass getting deflected by a current carrying wire? There is no bar magnet here. Where is the magnetic field coming from? That is how they all realized, oh, so that means that the electric current that we've been studying about for so long also has some magnetic field. Okay. Okay, so I hope that concept is clear to you now. Let's move on.